Say, say you are given this system in state space format. And maybe you don't like where the poles are. Maybe it's even unstable. Can you put it in this feedback configuration where we're going to say, for our purposes, this input R is a scalar. It's not a vector. It's just a single number. But what comes out is the complete state vector. And we're going to feed back that state vector, multiply it by a gain vector, where this gain vector k is 1 by n. If we do that, can we put the poles of this closed loop system where we want them? We have to assume we have access to the full state vector x. If there's a c to it, converting it to a scalar output, that would be downstream here. Let's look at where are the poles of this closed loop system. Now here's just the state part. Now this input u is r minus k times x. Multiply that out, we have this new system. Its characteristic equation is this. Can we pick a k so that we place the poles of this closed loop system where we want them? And the answer is yes, if the open loop system is controllable. Talked about controllability in a previous video. Let's take this example where n is two states. X is a vector of 2 states. Let's do 3 things. Let's check if it's controllable. We don't have any hope if it's not controllable of doing this. See if it's stable, and then find the k to place its poles exactly where we want them. In this case, somebody said poles should be at -3 plus or minus J4. Well, there's the A system, there's the B matrix, the A matrix, the B matrix. For controllability, we form the controllability matrix. This BAB. B part is here, 2, 1. The AB part, we have to do the multiplication. Here is A, here is B. Do that multiplication, you get 1, 5. Put that here. Now test that determinant. 10 minus 1 is 9. That is not 0, so it is controllable. Now on to part B. Is it stable? Is the open loop system stable? Well, here's the characteristic equation for the open loop system. It's S minus this guy, so it'll be S up here, S plus 3 down here, and these two guys change sign. That determinant is this, which factors get a pole at +1, another pole at -4. This pole at +1 makes it unstable. So it's unstable, but it is controllable. So we can find the k. How do we do that? Well, what we're going to do is equate characteristic equation. Here's the actual characteristic equation of the closed loop system with that feedback gain k in it. Here's what we want it to be. We put the poles at 3 plus or minus J4. That gives you this desired characteristic equation. So now we need to do this matrix arithmetic. We need to multiply out what the BK is. The B was this 2, 1, right? Here's the B. A is 1 by n. N is 2 here. And yes, you can do this matrix multiply. Will be 2 times the top row, twice this row, and on the bottom row is 1 times this row. So now we add this guy to what it was with just SI minus A. Here was the SI minus A part. Now we're adding this to it. We need to take that determinant. Is this? It's the product of these main diagonal guys minus the product of these off diagonal guys, which gives you that. Do some algebraic simplification, and you get this. Now all you do is equate powers of S. So we want this parenthetical term here to equal 6, and all this part back here, which is all a constant, to equal 25. That gives us 2 equations, 2 unknowns. Solve them, and that's our answer. Some of this gets a little tedious, and this is just a 2 by 2. There's a simpler way to do it. If the original state space representation is already in control canonical format, and it's even easier for higher dimensions than 2. I think I'll save this for another video. I think what I just already showed you in this video is pretty important and pretty awesome. I'll make an editorial comment. You might have thought throughout a lot of the rest of the course that there was a lot of approximation, graphical work, and you can only do one parameter at a time. And now all of a sudden you have this method that allows you to put poles exactly where you want and compute multiple games simultaneously. And that's kind of the beauty of modern control systems as opposed to classical control systems. In classical, it was done in an era where you didn't have computers to use so much and so easily. So doing matrix work was kind of cumbersome. Anyway, now we have state space, which allows some things to be done easier. And anyway, that's enough for this video.